Greetings. It's time for another vintage teardown. What I've got here is a Metrohm loop impedance tester made by Edgcumbe Peebles, and it's quite old. On the bottom it does have a test label from dated the 5th of the 4th 1979, so it's at least as old as that. It's a loop impedance tester, like I said. It's got a fuse holder there, it's got a small bulging plug there, and a test lead with a plug with no shroud on the pins. For those outside the UK, the pins are normally sleeved. And it also has a small wander lead as well, which can plug into a 3.5mm jack, or 1/8 of an inch jack probably, on the right. And yeah, so I don't want to test it actually in action just yet. I want to take a look inside and see what we've got before I go any further with that. So first thing I'm going to take a look at actually is this power lead, which is a, as I said, it's got a vintage Dura plug. And like so many old Dura plugs, which normally thread onto the cable before you put the plug on, someone's forgotten to put that on, as everyone used to do with these things. The new ones actually had a split in there, and they've gone, you know what, no, I'm going to cut the hole in the bottom to fit it on. Loads of these you'd find like that. And what's fallen out there is actually part of the fuse holder. It's broken off. Let's get the Dura plug alert 13 amp fuse out. So I'll want to replace that scrawny lead anyway. Should I replace the lead? I definitely need to replace the plug. So I've already taken a look at this. The sleeve and the tip are both actually joined together inside. So let's have a look at the tester itself. Now, unfortunately, I don't have the user manual for this. Looking online, the insulation testers, which look very similar to this, they had a slightly different case because they're provisioned for a battery. The user manual actually had a schematic in there to show how it was put together, so you could figure out how to repair it. Well, a rough schematic. It wasn't an entire schematic. Now then, there's a 0 set resistor control there. What else is holding this together? Something is. There might be a screw under there, so it may be that this isn't designed to be readily serviced. Yep, there's another screw there. Now it wants to come apart. There we go. What there is, that's the push button, and there's quite a bit in here. It's strangely, it actually almost feels heavier now. I've taken the lid off. There's a large meter, and there is circuitry behind the meter, and some tiny screws to get at that. There we go. And of course, the indicators being of this vintage, those indicators there are actually neons. So let's take this apart and try and trace it out. See how it's all put together. In fact, what I ought to do is record this bit so I can see how things come apart, ready for when I eventually need to put them back together again. So here's a close-up, sort of, and if you've got a big chunky, either a diode or a transistor, I'll have to find out from the I assume it's a transistor. There's a third connection on the stud there. So there's a small circuit here, there's a transformer, obviously there's the meter, which is getting a bit battered here, the neons, and this circuit board on the back. It should pull out, but I don't think it'll want to. And there's also this at the back, which is actually that's a high current variable resistor preset potentiometer. So yeah, let's work out what's what. Here's the board removed from its socket. This cap on the side here is dated 38th week in 1977. So that's given us the oldest age of some of the components. I think, based on the date code on the side of this, that code on the bottom, the April 79 one, is when it was actually tested as it left the factory. Because when this is in its big yellow packaging case, the carry case, I don't think it would have ever come out of that case. It wasn't really. It was a very snug fit. It wasn't meant to be pulled in and out. So anyway, this is the circuit board. And unfortunately, in getting this out, and it was quite a struggle to get this out, the needle got snapped. So I've only got half a needle now. There's the rest of it. But there we go. Not much else to see here. This is mostly the meter and the mounting base. You can see that big fat. I've looked it up. It's an SCR, it's a silicon control rectifier. You'll see in a moment when I bring the schematic up as to what that is. And a micro switch, which has 4 separate connections. There's a normally open, normally closed, normally open, normally closed. Not come across one of those before. Here's the schematic, and it took much longer for me to figure out what was going on than to actually trace this out. Connections wise, there's the 3-pin bulging socket, the live connection of which goes through a fuse holder with a 5-amp fuse, and the earth connection through a 3.5mm jack socket. If the test lead is inserted, then the bulging earth is disconnected and the test lead is used instead. Moving into the circuitry, a lot of which is wired point to point in a plethora of different colours, and first of all, let's get those neon indicators out of the way. The live to neutral one is easy, just a neon and a 220k resistor between the fused live and the neutral. The live to earth one is more unusual, in that although once again there's a 220k resistor and a neon, this time between fused live and earth there's also an 82k resistor in parallel with the neon. We'll come back to that shortly. There's a big old bolt mount SCR that's very difficult to find information on, but I stumbled across a datasheet which mentioned its ratings. This has its anode connected to the fused live connection and the cathode connected to the earth connection via a big 10 ohm 25 watt resistor, and we'll come back to that in a bit. Looking at the transformer, and I should say at the start that I may have got one or more windings reversed so that the phasing of the output will either be spot on or 180 degrees out. I've definitely got the centre tap placed correctly though, as that's based on resistance tests on the transformer windings. Whether or not the winding polarity is important remains to be seen, but I don't think it is in this instance. The primary of this transformer is connected by a red and blue wire to the fused live supply, and a white and grey wire to the neutral terminal of the input socket. On the secondary side, let's first look at the non-centre tap winding. The pink wire from this is half-wave rectified and smoothed by D4 and C4 before getting limited to 22 volts by ZD1 and current limited by R11. The anodes of ZD1 and D5 are going to be at the lowermost voltage of the circuit board, with current turning to the transformer via the blue and brown wire. This Zener limited supply goes to the drain of FET1 and also through a 2-tap potential divider formed by R9, preset VR2 and R10. R9, the whole of VR2 and R10 form a potential divider with 3.3k at the top and 2.8k at the bottom, therefore feeding a 10.1 volt share of the 22 volt supply to VR1 via 10k resistor R8. VR1 is the red knob on the back of the meter and is used to set the meter needle to infinity prior to testing. R9, a variable split of VR2 and R10, form a second potential divider ranging from 4.3 at the top and 1.8k at the bottom to 3.3k at the top and 2.8k at the bottom. So the output of VR2 will be preset to between 6.5 and 10.1 volts. I've measured the preset to find out what it's actually set to. Yellow-green to orange-brown measures 858 ohms, yellow-green to brown-blue measures 266 ohms, so that 44-year-old preset is a little on the high side overall. Anyway, if the Zen is putting out exactly 22 volts, then that gives us 7.3 volts. This goes to the board via the yellow and the green wire, and sets the voltage present at the cathode of D5. As this is also the anode of D3, which feeds the centre tap of the other secondary winding, this is setting the voltage of that entire winding relative to the first one. Now let's look at that other secondary. The brown wire hits D1, which half-wave rectifies it and feeds back out, where it goes through a normally closed switch contact, which returns via a white and green wire back to C1, charging it up. The other end of C1 goes to the orange and green wire, which bounces off one end of the big 25 watt resistor and ends up back at the transformer. The white wire is the centre tap, but because this connects to the cathode of D3, the resulting supply is going to be more negative than the orange and green wire, as it's taking power from the other half of the main cycle. It took me a while to get my head around this bit of the circuit, as it looked to me as though, as C1 charged, it would push C2 negative and cause it to explode. Of course, it's not C2's job to explode. C1 is the one that's made by reefer. If anything's going to be doing any exploding around here, it's that. I ended up drawing this subsection out on a second diagram just to try and figure it out, and only once I threw some example voltages on it did I get the light bulb moment and see what's going on. In this example, factoring in diode voltage drop but not factoring in transformer regulation and a low load, C2 is going to get charged to about 16 volts, C1 to about 32 volts, so the orange and green wire will have rails 32 above and 16 below it. So that's that cleared up. And given the voltage rating of the capacitors, I wouldn't be surprised if those are the voltages for that winding. So, back in the big schematic, so far we've got the top of D5 where the yellow and green wire connects at 7.3 volts, the top of C2 where the orange and green wire connects at up to 20 volts above that, and the top of C1 where the white and the green wire connects at up to 40 volts above that. That 22 volt Zener regulated supply isn't looking so high now, is it? I suspect VR2 is used to preset the voltage on the orange and green wire pretty close to that. So what happens when you power this thing up before the button is pressed? We can see that C1 will get charged up via D1 and one of the normally closed contacts, and without the button pressed, that's all it does. The other normally closed contact simply bypasses D2. This allows the orange and green supply via R1 to pull on the input to the JFET. Given that the diode would normally let it pull down anyway, I suspect it's pulling up, or at least pulling to 0, both of which will turn an N-channel JFET on. The more that JFET turns on, the higher the voltage across the meter. So in this state, the meter will be turned on, and the resulting needle position can be tweaked using the red knob on VR1. If the button is pressed, the short across D2 is removed. The meter will stay on unless the JFET's gate is pulled down through D2. Also, that charging circuit is opened, disconnecting the capacitor from the supply, and a second contact is closed, dumping C1's charge via a violet wire into R5. This forms a potential divider with R4, the midpoint of which goes out on a blue wire straight to the gate of the SCR. This triggers the SCR, which now puts the 25 watt 10 ohm resistor in between live and earth, and it'll keep on doing that until the capacitor is discharged. That current flow is going to result in a potential between the orange and green wire on the one side of the resistor and the green wire on the other, with green being the lower of the two. Both of these connections head off to the board. The orange and green wire, we know, is held at a preset voltage of around 7.3 volts plus whatever C2 charges to, so that's going nowhere. If anything special is going to happen, it'll be with the green wire. The lower the earth impedance, the lower the voltage at this point will be. The easy way to get your head around this is to imagine that the earth connection was an open circuit. Infinite resistance, infinite impedance. In this instance, there'd be nothing pulling down on R13 at all, so both ends would rise to mains potential when the SCR is fired. If the impedance was 0, there'd be mains at the SCR end and 0 at the earth end. Now, as we can see, that goes to a 220k resistor, and the other end of that is the neutral connection. Incidentally, this may explain the presence of the 82k resistor across the neon. Without it, the two 220k resistors, one to live and one to neutral, would be enough to light the neon. But that 82k resistor will reduce the neon voltage to around 35 to 40 volts, so it's not going to strike on just a live and neutral connection. It's going to need more than that. Besides the 220k resistor though, the green wire goes to a 1k resistor to the cathode of D2. This is still getting pulled, presumably up, by R1, and that's just 33 ohms. Remember what I said though, the lower the earth impedance, the lower the green wire voltage will be. With the SCR fired, orange and green is now at mains potential, albeit rectified. If earth impedance is infinitely high, green will be as well, and R1 will keep doing its thing and holding the meter in place. If earth impedance is 0 though, the green wire will put 340 volts into that divider to give minus 10.9 volts, opposing whatever voltage is present at the top of C2. The lower the voltage at the midpoint of the divider, the lower the voltage at the gate of the JFET. As long as this is negative, then the lower it is, the further off the JFET will go. The further off the JFET goes, the lower the voltage on the orange and blue wire. The lower this is, the lower the meter needle goes. This is all going to happen in a split second, as the 10 ohm resistor would burn up if it wasn't for the SCR quickly shutting off the power when its gate capacitor discharged. The lowest voltage, and therefore the lowest reading, that's reached will be stored in C3 though, so the JFET should hold its position for a while, at least until you let go of the test button, at which point D2 gets bypassed, C3 refills, and the JFET sets the meter to full scale again. And that's it. Or at least I think that's it. I could be completely wrong. Some of my figures may be out here and there due to diode volt drops, but you get the idea. Right, let's try and get this back together. I can't test this in the house because all the circuits in the house are protected by RCBOs. So if I plug this in and push the test button, it's just going to trip the RCBO anyway. So I do have two other options though. Let's go take a look. What I could do is connect it to my mains conditioner, because this also runs as an isolation transformer. And what I then need to do to provide a false earth, if you like, is use this neutral to earth link plug, which would force neutral to earth, so then it's got something it can reference back to. Otherwise it would be an unearthed connection. It's going to be an open circuit. It's going to fail the test. Or I could use this. It's not had to run for a while, and if I was going to knacker anything up with the test, I'd rather it be this than the mains conditioner. I better test the supply first, make sure it's suitable. Back to plan A then. It's more like it. Will it go bang without the test button? No, it's gone completely off the scale. And what happens if it's tested? That worked. You bring the camera to a different angle so you can see what happens with the needle. So you can see at the moment it's at the infinity mark. You press the button and it drops to show you the loop impedance, as was. That has actually disconnected itself now. That's just holding itself at the voltage it saw, the loop impedance it saw. Let go, and back to normal. So there we go, a vintage Metrohm loop impedance tester, still working strong over 40 years later, albeit with a snap needle. Thanks for watching.